Section 5.4. We're going to talk about counting. Okay? We do need to write out or type out. You do kind of need to know the fundamental principle of counting. This, of course, can be found in your textbook. I'm sure they're going to ask you some kind of homework questions about it. If an operation can be performed in M ways, if an operation can be performed in M ways, and a second operation can be performed in N ways, then the total number of ways to perform the sequence of two operations is M times N. Okay? It's the fundamental principle of counting. If a sequence has a little add-on, if a sequence of several operations is to be performed, the number of ways to perform this sequence is found by multiplying together the number of ways to perform each of the operations. Okay, let's look at example 1. When ordering, and we kind of start off with examples after we get through with that, because the easiest way to learn to count is to practice, just like with small kids. Okay, it's the same thing. It's not the same process by any means whatsoever, but practice helps us get better. When ordering a certain type of computer, there are 3 choices of hard drive, 4 choices of, or 4 choices for, I'm sorry, 4 choices for the amount of memory, two choices of video card, and 3 choices of monitor. Okay? In how many ways can a computer be ordered? Okay? So, guys, this is like the Sonic drink question. Okay? There you go, Sonic, how many different ways can you order a drink? You know, you got the choice of Coke, Diet Coke, Dr. Pepper, Diet Dr. Pepper, all those. Then how many add-ons you can put in there. You want light ice, easy ice, extra ice, that kind. It's one of those kind of questions. That's what these questions are like, okay? So when we order a computer, there are 3 choices of hard drive, 4 choices for the amount of memory, 2 choices of a video card, and 3 choices of a monitor. In how many ways can a computer be ordered? Okay, well, so here's what I do. I go, all right, so I've got a slot for the hard drive, okay? The number of hard drive. I'm going to multiply that times my slot for the memory. Then I've got a slot for the video. Then I've got a slot for my monitor, okay? So, how many choices of hard drives do I have? 3, okay? How many choices of memory? How many available amount of memory are there? 4. Video cards? 2. And monitors? 3. Multiply all those together. That gives me what? 12 times 6, which is 72. That's how many different ways you can order your computer. There are 72 different ways. That's all there is to it. Okay? Example 2. Okay, a quiz consists of 3 true-false questions and 2 multiple choice questions. With 5 choices each. How many different sets of answers are there? Okay. So, here's what I do. There's 3 true false. There's 2 multiple choice, right? Okay, so I got a true false slot. 1 question's a true false. 2nd question's a true false. A 3rd question's a true false, right? Then I got a multiple choice question. And then I got a multiple choice question. Okay, because it wants to know how many different sets of answers are there. So you might get one student that goes true, 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 A, B, right? And then you might get one that goes true, false, true, C, D. Okay, so what they're wanting to know is how many different possibilities of answers are there, like combinations of answers. And I'm very hesitant to use the word combination because we talk about combinations in a minute with permutations. But like if you listed out all the possible ways a student could answer, how many are there? That's what they're asking you. Okay, so on that first question, there's a possibility of how many answers? 2, because it's true, false. So there's only two Two possibilities. Student can't answer anything but true or false. How about the second one? How about the third one? How about the fourth one? Yep, and the fifth one. Good. Okay? If I multiply all that together, that gives me what? 200, that is correct. Okay? Because I got 5 times 2 is 10, and 5 times 2 is 10. 10 times 10 is 100. 100 times 2 is 200, right? Okay, good job. All right, now here we get to our, here's a definition, okay? The word permutations, this one is actually important. The word permutations is another word for ordering. Okay? When we count permutations, we are counting the number of different ways that a group of items can be ordered. Okay? The most important part of that definition is the word permutations is another word for ordering. Okay? In example 3, you'll see what I mean. We have 5 runners run a race. One of them will finish first, another second, and so on. In how many different orders can they finish? Okay. So, we got 5 runners, we got 5 places, right? Okay, so that means we have a first place, a second place, a third place, fourth place, fifth place. This time, guys, ordering does matter, right? Because if Misty's first and Raina second, then that's different than Raina being first and Misty being second, right? Yes, so ordering matters here. So, everybody's running. The 5 people are running. How many different people at that point, well, everybody's running, trying to get there. How many different options are available for first place? 5. There's 5 people in the beginning. There's 5 people running for first. That's what they're all doing. They're all competing for first. There's 5 people. Okay? But first place is now taken. So, how many people are available for second place? Sorry, for second place. 4, right? There's only 4 people left because 2 people are now done. First and second place are done. Okay, all that's left is place 3, 4, and 5. How many people are left that could take third place? 3. Okay, then how many people are left for fourth? 2, and then there's the 1 person for 5th place, right? So these are the different possible ways that this could take place. Ordering does matter. Okay? What do we get? 120, good. So we say there are 120 permutations of the 5 individuals. Okay? All right, let's look at a little definition. This one's nice. N factorial. And it is represented with your number and exclamation point. So N exclamation point. This means we say N times N minus 1 times N minus 2, ... Okay, and so on. Guys, all that means is if I give you 5 with an exclamation point, that's 5 factorial. That means 5 times 4 times 3 times 2 times 1. Okay, it's just a notation because some old dead math dudes didn't want to write all that out. So they were like, ha, let's put an exclamation point out there. It's going to mean 5 times 4 times 3 times 2 times 1. I don't have to write all that. Okay. That brings us to example 4. We're not going to finish this. Okay. Example 4 says 10 runners enter a race. Okay. The first place finisher will win a gold medal. The second place finisher will win a silver medal. And the third place finisher will win a bronze medal. How many different ways can the medals be awarded? So I'm going to abbreviate that a little bit. First place is gold. Second is silver. And third is bronze, right? Okay? In how many ways, in how many different ways, can the medals be awarded? Okay, well, guys, there's 10 folks running, and we only have 3 places. Okay, we've gone from elementary little field day where everybody wins something to now we're doing track in high school where we're only going to give 3 places away. Usually we have more than 10 people because we got more than 1 heat. But, okay, how many people could get that first place marker? 10. Okay? Then how many could get the second place? 9. And how many could get the third? 8. Gives me a possibility of 720 different ways to award those 3 medals out of 10 people. Okay? This is referred to as a permutation of 3 items chosen from 10. So it's 3, choose 10. Now, you'll notice we've written something like that each time, okay? It's because in the next part, we show our notation. We talk about permutation again. So, we make permutations a little more mathematical this time, and we say a permutation of R items chosen from N items is an ordering of the R items. It is obtained by choosing R items from a group of N items, then choosing an order for the R items. Okay? The number of permutations of R items chosen from N is denoted NPR. And that will equal, here's where your factorial comes in, N factorial over N minus R factorial. Okay? Guys, in the example that we had, it makes sense, okay? Because we chose 3, so right here, I'm gonna come up here. We chose, this was 3. We had what, 10 items? 10 choose 3, right? 10 choose 3 is going to equal 10 factorial over 10 minus 3 factorial. Okay? I'm actually going to circle this. I'm going to put this down here. You guys don't have to write this down. I'm just showing you how example 4 would have been worked. Okay? So, well, 10 factorial is really 10 times 9 times 8, 7, 6, 5, 4, 3, 2, 1. Well, 10 minus 3 factorial, that's 7 factorial. Okay? And guys, 7 factorial is really 7 times 6 times 5 times 4 times 3 times 2 times 1. And what happens when we have 7 over 7, that gives me 1. 6 over 6 gives me 1. They start to simplify. They start to cancel out. So, we got 7 goes, 6 goes, 5 goes, 4, 3, 2, 1. Left me with 10 times 9 times 8, which was my 720. Now, I'm going to be honest with you. For me, it's easier to make the slots and go, well, that's 10 times 9 times 8. I got 10 people that can go here. And as long as the problems are simple, it's not very difficult. You can do like that. You don't have to use the formula. I'm not grading you on, oh, did they set up 10 factorial over 10 minus 3 factorial and get 10 over 10 factorial over 7 factorial? I'm not looking at that. If you can do the problem and it's simple enough for you to make your slots and go this times this times this, and you get the same answer, I'm counting it right. Now, they will become a little more complicated, And honestly, your calculator has an NPR function. So literally all you have to do is put it in there, and you don't have to do any math work whatsoever. If you look at your calculator, and we look over here at, okay, if you will go to stat, like when we would put if you'll go to stat, nope, it's not at stat. Let me think. Yeah, stat calc. No, it's not. Lord, math. Go to math. Go to math. Everybody see math? He's under alpha. Go over to probability, prob. And everybody see number 2, NPR. If you'll hit NPR, and then you literally can just type in the 10, and then it moves it. You can move along over here, and what did we choose? 3. And you hit enter, you get 720. And you have to multiply those slots together. Okay? If you noticed on math and probability, your PRB, you also saw an NCR. We do that in a minute when we do combinations. That function is a lot easier, more applicable, because there's a lot more math involved if you don't use that button on your calculator. Okay? But there's your NPR function. Does it come up with parentheses?
No, it comes up with NPR.
Bring it here. Let me see real quick. You probably have to put the 10, 3, Oh, okay. So what you do on that one, if you've got this, guys, do 10 first, and then do your math, prob. No, go back over. I'm moving too fast, even though I'm not moving fast. So then it's 10, choose 3, then that should work. Yeah, there you go. Yeah, no problem. Okay, let's look at number 5. Five lifeguards. Are available for duty on Saturday. Okay, there are 3 lifeguard stations. In how many ways can 3 lifeguards be chosen and ordered among the stations? Okay. So, how many is your total set? What's in? What's in? How many total lifeguards do you have? 5. And how many are you choosing? 3. Yep. So, calculator-wise, this is just 5P3. Okay? if you work it out, 5p3, that is 5 factorial over 5 minus 3 factorial. So that's 5 times 4 times 3 times 2 times 1 over 2 times 1, which is going to give me 60. Did we get 60 when we put it in the calculator? Yep. Okay, if you're doing it with the slots, if I have station 1, station 2, station 3, how many lifeguards are available for station 1? 5. How many are now available for station 2? 4. How many are available for station 3? 3. And that gives me 60. So, you get 60, whichever way you do it. You are allowed to use a calculator, so if you want to just use your handy dandy calculator, I got no problem with it. Okay. Example 6. The 5 lifeguards are named Abby, Bruce, Chris, Donna, and Esmeralda. I'm going to read the problem to you first. Okay. Of the 3 lifeguard stations, 1 is located at the north end of the beach, 1 in the middle of the beach, and 1 at the south end. The lifeguard assignments are made at random. What is the probability that Bruce is assigned to the north station, Donna is assigned to the middle station, and Abby is assigned to the south station? Okay. So, we have our 5 lifeguards. All right. And they are Abby, Bruce, Chris, Donna, and Esmeralda. Okay? We have 3 stations. It is north, middle, and south. Okay? They're made at random. We want the probability that Bruce is assigned to the north station. Donna is assigned to the middle station, and Abby's assigned to the south station. So, how many possible outcomes of the 5 people being assigned to the 3 stations were there? This is kind of like from 5. 60, right? Okay. So we know there are 60 possible outcomes of the 5 people, being assigned to the 3 stations. Okay? Now, so there's 60 possible different scenarios. So you could get a Bruce, Chris, Donna. You could get a Bruce, Donna, Esmeralda. You could get an Abby, Bruce, Chris. You could get the Abby, whoever, right? Whoever they're wanting. So what they're asking you is, what's the probability that you're going to get Bruce at north, you're going to get Donna in the middle, and we're going to get Abby at south. Okay? Well, can we get Bruce at north, Donna at middle, and Abby at south more than one time? No. That only happens once. If I assign Bruce to north, then Bruce is at north. Right? He can't come back and be at the middle also. And he can't come back and be at the south. The same thing happens with if Donna gets assigned to the middle. So what it's saying is if we had listed out in the top with all 60 of them, we would have listed the different combinations. We'd have gone Bruce, Donna, Abby. Bruce, Chris, Abby. Bruce, Esmeralda, Abby. Then we might have had Donna, Abby, Bruce. Because Donna, Abby, Bruce is not the same as Bruce, Donna, Abby, is it? If I say Donna, Abby, Bruce, is that the same as Bruce, Donna, Abby? No, because who's at north now? Donna. Who's in the middle? Abby. And Bruce is at south. So that's a totally different combination, right? It's a different permutation. Order matters, guys. So how many times am I going to see Bruce, Donna, Abby come up out of that 60? In that order, that exact order. How many times I'm going to see Bruce at north, Donna in the middle, and Abby at south, those three together in those exact places out of those 60? One. You see it? One. So the probability of the Bruce, Donna, Abby combo right there is 1 out of 60. Okay, it's like if I had 3 coins, guys, and I was flipping each 3 coins, and one's a penny, one's a nickel, one's a dime, and I want it to come up head, head, tail, exactly. That combo together, that's the only way I win money, is if I get a head, head, tail. How many times does that come up? Only once. Only once am I going to get a head on a penny, a head on a nickel, and then a tail on a dime right there together, like that, in that order. That doesn't happen again. Okay? Out of however many different possibilities, and that would be probably 3 to the, yeah, you don't have to worry about that part. Okay? That's why that's 1 out of 60. And it's to try to get you to understand that the order does matter here. Picking Bruce to go to north, Donna to be at the middle, and Abby to be at south does matter. Okay, guys, so we're going to go ahead and finish up section 5.4. It looks like we finished exercise 6. So we had an answer of 1/60 for that. If we are on example 7, we have a committee of 8 people must choose a president. Okay, a vice president, and a secretary. In how many ways can this be done? Okay, so this, once again, this is a permutation. Order does matter. Whoever is picked first, and that's the president, that's different than if that person is picked second, because that would be the vice president. And of course, it would be different if that person was picked third and was the secretary. So we're doing a permutation. So that's 8, choose 3. So we have, of course, 8 factorial, or we can go ahead and write that formula out. I have n factorial over n minus r factorial, which gives me 8 factorial over 8 minus 3 factorial, which does give me 8 factorial over 5 factorial. Okay, that's going to, of course, then I'm going to go ahead and write this out. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that is all over 5 times 4 times 3 times 2 times 1, because I know we went through that fairly fast last night. 5 divided by 5 is 1, so they simplify to 1. 4 over 4 is 1. 3 over 3 is 1. 2 over 2 is 1. And 1 over 1 is 1. So I'm left with 8 times 7 times 6, which does give me 336 ways. You could also put that in your graphing calculator. It's easiest for me on here with Desmos. So I'm going to use my Desmos here, and anybody can use Desmos. And if I go to NPR, I click that. So I found that under functions, and I went down actually to number theory and found NPR, and I'm going to say 8, comma, 3. And that does give me 336 ways. Okay, so that's example 7. If I look at part B of example 7, it says 2 of the committee members are Ellen and Jose. Assume the assignments are made at random. What is the probability that Jose is president and Ellen is vice president? Okay, so here's what we're looking for. We know that we have 3 positions, right? We have 8 people. We have 3 positions. We have the president. We have the vice president. And then we have the secretary. So here's the deal. We want Jose to be president each time, and we want Ellen to be vice president each time. Okay, we know that there are 336 total permutations with the 8 people, but now Jose and Ellen have taken up president and vice president. So we don't have 8 people anymore to choose from. So Jose and Ellen could be president and vice president, and then we could have person 3 as secretary. We could have person 4 as secretary, or we could have person 5 as secretary, or 6 as secretary, or 7 as secretary, and then finally 8, person number 8 as secretary. Okay, but each time Jose and Ellen have to stay in their spots. But these are the different possibilities of Jose being president, Ellen being vice president, and then one of the remaining 6 people being the secretary. Okay, so how many different possibilities are there? Well, that's 1, 2, 3, 4, 5, 6. 6 out of a total of how many? Well, we found in A that there were 336 total permutations. 6 of those 336 actually have Jose as president and Ellen as vice president. So that's going to be the probability of Jose is president and Ellen is VP. Okay, 6 out of 336 is going to give me 1 out of 56. Okay, that's part B. Let's look at part C. C says, what is the probability that either Ellen or Jose is president and the other is vice president? Well, okay, let's think about it. We've already done Jose with president and Ellen with vice president. There were 6 of those. Well, there's going to be 6 of the reverse also. So, Ellen as president and Jose as vice president. Okay, then we have the 1, 2, 3, 4, 5, 6 other people. So that's going to give me 12. There's 12 scenarios where either Jose is president and Ellen is vice president, or Ellen is vice president, or Ellen is president and Jose is vice president. So now I have 12 out of 336, which is going to give me 1 out of 28. Okay? All right, we need to talk about when to choose combinations. Okay? Use combinations when the order of the chosen objects doesn't matter. Okay? Use permutations when the order does matter. Okay, we've been doing permutations, guys, where the order does matter. Now, if the order doesn't matter, then it's known as a combination, and we use a C. It's NCR, and this equals N factorial over R factorial times N minus R factorial. Okay, so let's kind of look at the difference between a permutation and a combination. So if I have a permutation, think of something like this. I have 3 people. Okay, A, B, C, and I want to give away a $100 bill and a $50 bill. The first person I choose gets the 100, and the second, the 50. And of course, if you don't get chosen, you don't get anything. Okay, so here, order matters. Okay, we have the $100 bill, we have the $50 bill. So A could get it the 100 and B could get the 50. A could get the 100 and C could get the 50. B could get the 100 and A could get the 50. B could get the 100 and C could get the 50. C could get the 100 and A could get the 50. Or C could get the 100 and B could get the 50. Okay? So order matters. In this case, since order matters, it's a permutation. And we use N, P, R. Well, N is 3. R is 2, so this is 3. Let me write the formula. NPR, so I have N factorial over N minus R factorial. So this is 3, choose 2. So that's going to give me 3 factorial over 3 minus 2 factorial, which gives me 3 factorial over 1 factorial, which just is 6. Okay? Now, let's look at it if it were a combination. So, if I'm talking about a combination, I have 3 people. A, B, C. And I want to give away a $100 bill and a $100 bill. Okay? Order doesn't matter here when you draw the person. We're looking at who gets a $100 bill. No matter if you're picked first or you're picked second, you still get a $100 bill. So I could pick A first and I could put B second. They're each getting a $100 bill. So that means I don't need to count BA. They're still both just getting a $100 bill. So I can have AB gets a $100 bill, AC could get a $100 bill, or BC could get a $100 bill. So that's a combination. So it's NCR, which is N factorial, over R factorial times N minus R factorial. Well, that's 3. Choose 2. So that's 3 factorial over 2 factorial times 2 minus 1 factorial. Oh, no, I'm sorry. Times 3 minus 2 factorial, which is going to give me 3 times 2 times 1 over 2 times 1 times 1. So the 2's and some 1's go away. It leaves me with just 3. Order didn't matter there. The 2 I drew both got a $100 bill, so it didn't matter if I drew you first or I drew you second. Let's look at example 8. "30 people attend a certain event. And 5 will be chosen at random to receive prizes. The prizes are all the same. So the order in which the people are chosen does not matter. How many different groups of 5 people can be chosen? Okay, so in example 8, I have 30 people attend a certain event, and 5 will be chosen at random to receive prizes. The prizes are all the same, so the order in which the people are chosen does not matter. How many different groups of 5 people can be chosen? Okay, so since order doesn't matter, that means it's a combination. So I have n choose r. Okay, I know that's n factorial over r factorial times n minus r factorial. In this particular case, I have 30 people and I'm choosing 5. So I've got 30 factorial over 5 factorial times 30 minus 5 factorial. That's 30 factorial times 5 factorial over 25 factorial. Guys, when I write out 30 factorial and I write out 25 factorial, 25 down to 1 are all going to simplify down to 1. So this leaves me with 30 times 29 times 28 times 27 times 26. And then I have, of course, 5 times 4 times 3 times 2 times 1. Guys, I actually go ahead and simplify this by hand. That's a 5. That's going to be a 6. 4 will go into 28 7 times. 3 will go into 27 9 times. And 2 goes into 26 13 times. So you have 6 times 29 times 7 times 9 times 13. That is going to give us 142,506 different ways the people can be drawn. Of course, you could have done that on your calculator. We could have gone back over here. We could have gone to functions, gone down to number theory. We should also have a combination there. So we've got NCR. We had 30 people. We were choosing 5. Order didn't matter. And of course, we get 142,506. Okay. So that's example 8. Let's look at example 9. Okay, example 9 is actually a continuation of example 8. So it says, of the 30 people in attendance, okay, 12 are men and 18 are women. Okay, A says, what is the probability that all the prize winners are men? Okay. Okay, order doesn't matter here, guys. The thing is, you need to draw 5 men. Well, how many are men? 12. How many are we choosing? We're picking 5, right? We want them to be the winners. So this tells you how many different combinations of men there are. When I say 12, choose 5, I need, out of the 12 men, I'm going to pick 5. And how many different combinations could I have? Well, that's going to give me 12 factorial over 5 factorial times 12 minus 5 factorial. That gives me 12 factorial over 5 factorial times 7 factorial. Okay, well, the 7 and down are all going to cancel out. So I have 12 times 11 times 10 times 9 times 8 all over 5 times 4 times 3 times 2 times 1. 5 goes into that 10, 4 goes into the 12, 3 goes into the 9, 2 goes into the 8. So I have, it looks like 3 times 11 times 2 times 3 times 4, which is going to give me 792 combinations of 5 men out of 12. Write that down if you need to. Now, that's not my answer. Okay, they're asking me what's the probability that all 5 will be. Well, we know total number of combinations, including the women, and then we pull some winners are women, some are men, some could be all women, that there are a possibility of 142,506. Okay, that's the total number of combinations possible for drawing winners. Well, of those 142,506, 792 of them consist of all men. Okay, so the probability of all men being drawn is going to be 792 out of 142,506. Okay, so when we put that into our calculator, we get 0.005577, which is approximately 0.0056. Guys, that's less than a 1% chance that all 5 winners are men. Okay? That is A. Let's look at B. B says, what is the probability that at least one prize winner is a woman? Okay, so this goes back to, I think our chart in 5.3 or 5.4. Oh, no, this is 5.4, so probably 5.3, where we have at least one. So the probability of at least one woman will equal 1 minus the probability of no women. Well, the probability of no women is the same as the probability of all men, right? So this is 1 minus the probability of all men, okay, which we found that in part A. So this becomes 1 minus 0.0056, and that's going to equal 0.9944. So there's a 99% chance that at least one of the women, one of the prize winners will be a woman. Okay? And then we have example 10, last one. Example 10 says 8 college students have applied for internships at a local firm. 3 of them will be selected for interviews. In how many ways can this be done? Now, the first thing we need to ask ourselves, does order matter? They're just selecting 3 people for interviews. It doesn't say that you win something if you get picked first or you get a certain person. It says you're just picking for interviews, so order doesn't matter. You just care about that you get picked. So this is a combination. So we have 8 college students and we are picking how many? 3 for interviews. So we have 8, choose 3. So I've got 8 factorial over 3 factorial times 5, 8 minus 5, 8 minus 3. How about that one? 8 minus 3 factorial. So I've got 8 factorial over 3 factorial times 5 factorial. Those 5s are all going to go down. So that's 8 times 7 times 6. And that leaves me with 3 times 2 times 1. 3 will go into 6 2 times. 2 will go into 8 4 times. So I have pretty much 8 times 7. So I have 56 over 1. So there's 56 different ways to choose those 3 people out of 8. Okay. Part B says, for the 8 students are from Middle Georgia State University. 4 of the 8 students are from Middle Georgia State University. What is the probability that all 3 of the interview students are from Middle Georgia? From Middle Georgia State University. Okay. All right. Well, we know there are 56 total different ways, but we want to know what's the probability that all 3 of them are from this one university. So we've got 4 from the university and we want to choose 3. So that's going to be 4 factorial over 3 factorial times 4 minus 3 factorial, which gives us 4 factorial, 3 factorial, 1 factorial. Well, that just gives me 4. Okay? So there's 4 different ways that we can pick 3 students out of 4. Okay? So let's find the probability of doing that. Well, out of these 56, 4 of those contain all Georgia State University kids. Okay? So the probability that all are from MGSU is going to equal, we have 4 out of the total 56, which gives me 0.0714. There's only about a 7% chance. That is the same thing. I think this problem had us listed as a fraction, which is 1 over 14. So either one. Okay? And that is the end of our 5.4 notes.